Sounds are produced by vibrating objects. The vibrations of a sound source cause the surrounding air molecules to move back and forth, creating a series of alternating regions of high and low pressures. A sound wave is basically a pressure wave. It propagates in the form of fluctuations in air pressures. The loudness of a sound is determined by the amplitude of sound waves, which represents the strength of vibrations produced by the sound source. The stronger the vibrations, the higher the amplitude of sound waves, the louder the sound. The pitch of a sound is related to the frequency of sound waves, which indicates how fast the sound source vibrates. The higher the frequency, the higher the pitch. Frequency is measured in hertz. A young human ear can detect sounds in the range of 20 to 20,000 hertz. Some animal species can hear frequencies well beyond this range. Hearing is the process by which the ear transforms sound vibrations into nerve impulses that can be interpreted by the brain as sounds. The human ear has 3 distinct regions, called the outer, middle, and inner ear. The outer ear funnels sound waves through the auditory canal to the tympanic membrane, also called eardrum, which separates the outer ear from the middle ear. The eardrum is attached to a chain of 3 small bones in the middle ear, called the ossicles, the malleus, incus, and stapes. Sound waves cause the tympanic membrane to vibrate, and the vibrations are transmitted through the 3 bones to the oval window, where the inner ear begins. Since the eardrum is much larger in area than the oval window, the sound pressure that arrives at the oval window is much greater than the original pressure received by the eardrum. This amplification is essential for the stapes to push against the higher resistance of the fluid in the inner ear. The organ of hearing in the inner ear is the cochlea, essentially a long tube that is coiled up in a spiral to save space. The cochlea is composed of 3 fluid-filled chambers. The central chamber, known as the cochlear duct, is where mechanical vibrations are transformed into nerve impulses. There are 4 rows of hair cells within the cochlear duct, supported on the basilar membrane. The movements back and forth of the stapes push on the fluid in the cochlear duct, causing the basilar membrane and the hair cells to move up and down. These movements bend the cilia of hair cells, opening the mechanically gated potassium channels on their surface. Influx of potassium depolarizes the cells, stimulating them to send nerve impulses to the cochlear nerve and on to the brain. Our ability to differentiate sounds of different loudness and pitch depends on the ability of the cochlea to respond differently to different amplitudes and sound frequencies. Louder sounds cause more hair cells to move and generate greater nerve signals to the brain. Different frequencies stimulate different parts of the basilar membrane, which acts like a set of piano strings. The basilar membrane is narrowest and stiffest at the base, near the oval window, and widest and most flexible at the far end. High-frequency sounds with more energy can move the stiffer part of the membrane, while low-frequency sounds can only move the more flexible part. Thus, high-pitched sounds excite nerve fibers that are closer to the oval window, while low-pitched sounds send signals through the fibers at the far end. Thank you for watching. If you like our videos, be sure to check out our new Patreon page. Patreon is a simple way for you to contribute to our production and get great rewards in return. Join us to make videos like these happen.